A tree is a special type of a graph, and a binary tree is a special type of a tree where every node has somewhere between 0 to 2 children nodes. Binary trees are a very common topic in software engineering interviews, but in addition to that, in your career you actually use concepts that build on top of binary trees. To create a binary tree, we first need to define the class. I've named it node. You can name it tree node or anything that you like. This has a value that we can pass to it, and it has two references to its left and right node. Initially, they're both set to none because we create the node and then gradually connect the nodes that we create after. So let's create this first node. So I just need to instantiate this class, and this 2 is getting passed as the value. So now root is this object. So this is the node object sitting at a memory location. Its value is 2, and the left and right node currently are just none. Now let's create those two nodes. So we want to create 5 and 1 and connect them to this root node. So I can create one node called node 1 with a value of 5, one node called node 2 with a value of 1, and the way I can connect them is just root left equals node 1 and root right equals node 2. Now I will print them with just some spaces so they look similar to what we have up there, and you can see that the values are exactly what we have. So root, root left, and root right. Now let's continue creating the rest of them. So this follows exactly the same pattern, and I'll let you trace the code and connect the dots. And again, I'm printing everything with some spaces so they look the same as the tree that I have. There are a few ways to traverse a tree. The first one is depth first search, or DFS for short. The idea is that we want to go as deep as possible and hit the end and then go back. Again, once we hit the end, we go back and go as deep as possible. So the function has 3 parts to it. The first part is the check for if we have hit the end. So if node is none, we return. The second part is what we want to do inside there. So here I'm just printing it out. We could maybe sum the values or do any other operations that we need to do with the node values. And then the third portion is just passing the left node and then the right node to the same function. So that's what makes this a recursive function. So if I call this with the root node, you see that these values are being printed in the same order that you see in yellow. Now let's say I wanted to sum the nodes. So the function to sum the nodes is pretty much the same as this DFS function. The only thing that I'm changing here is I'm defining a total because I want to just reuse this value. Basically, this will work as a global for this function. So non-local basically tells this function that this is defined outside of the scope of this inner function, and I will just add to that same value each time that I reach a node. The first part is the check to see if we have reached the end, and then instead of print, I'm just adding the value of that node to my total and then checking the left and right node. So if I run this, you see that I get 26, and if we just sum this real quick, 2 and 5, 7 with 1, 8, 8 and 8, 16 and 3, 19 and 7, 26. So that checks out. The second way that we can traverse a tree is called BFS, so breadth first search, which is pretty much the opposite of what depth first search does. We want to check the closest nodes first, so we want to go as wide as possible before we go deep. So in this case, I will first check root, and then the left node, and then the right node. And again, for the left node, left and right of that one, and then for the right node, there's no left, so just the right one. Now, to do BFS, we need a queue, and the perfect data structure for that in Python is the dict, which we can import from the collections module. So I'm defining this queue and just putting the root in there. And then I create a while loop that will continue as long as my queue has some element in there. So initially I have my root in there. So when the queue element is popped out, this node is my root. then I do the sum or print or anything I need to do with that node value, and then I enqueue the left and right node if they exist. So if node left exists, then I append it to the left of my queue. Same thing with the right node. If it does exist, I append it to the left of my queue, and this will continue until there's no more nodes left in that queue. If you're still not super clear on BFS, check out this link. I created some visuals that I think will help you see what happens behind the scenes as you walk through the code line by line. Level order traversal is really what the name suggests. We go over the nodes level by level. And the way to do it is very similar to BFS. The only difference is that I create a for loop which iterates exactly as how many starting nodes as we had in the queue. So let's go into this a little deeper. So initially, when I have only one element, this for loop will only happen once. So the length of the queue is 1, so this happens exactly one time, and I print the node value, and this print function just prints a new line so you can see what is happening per iteration. And then the second time, because I have enqueued 2 more nodes, so the length of my queue is going to be 2, so this will happen twice, and so on. So the last time this for loop will execute 3 times. So this for loop will just separate each iteration of this outer loop by how many times, exactly how many nodes we had in that queue when we started the for loop. So let's print this out. So you see that at each iteration, we are printing exactly the nodes that we had in that level. When talking about binary trees, there are some terms that it's good to be familiar with, but don't worry too much about memorizing these definitions. A full tree is a tree that each node has 2 children, except the leaves. So you can also define it as a tree where each node has 0 or 2 children. A complete tree is a tree where every level is filled except the last one, and all of them are filled from left to right. So this first one is not a complete tree because the left portion is empty and the right portion is filled. This one is complete because everything is filled from left to right. A tree can be full and complete. So here, every node has 0 or 2 children, and all the levels are filled except the last one, but they are filled from left to right. Now, a tree can be full and complete and still not perfect. A perfect tree is a tree where all of the nodes have 2 children, except the leaves again, and they all have the same depth. So all the subtrees have the same depth. A balanced tree is a tree where the difference between the left and right subtree for every node is not more than 1. So the left subtree of this root node has a depth of 2. On the right side also it has a depth of 2, so that's fine. If the difference was 1, that would still be okay, but in this case where the difference is 2, that's not a balanced tree. So we could balance this more by putting these 2 nodes on the left side. So right now the left subtree here has a depth of 0, the right subtree has a depth of 2. A binary search tree is a type of binary tree where every node in the left subtree is smaller than the parent node, and every node in the right subtree is greater than the parent node. One thing to pay attention to is that we're talking about the whole subtree, not just one node. So here 4 is smaller than 6, but every other node here is also smaller than 6. So I couldn't have 4 and then 7 here because the whole subtree has to be smaller than the parent node. Same for the right nodes, so all of these nodes are greater than 6. And then this is true for every node for this whole tree. So if you go down here, every node in this subtree is greater than 4, and every node on the left is smaller than 4. The value of a binary search tree is that I can find elements a lot faster. Basically, time complexity for finding a node is only log of n. Let's say I'm trying to find a node with a value of 5. I start from the root, as soon as I see the value is 6, I can eliminate everything to the right of this node, because I know in a binary search tree, all the values that are smaller than this node are going to be on the left of it. And then I reach 4, then again I can eliminate everything on the left because 5 is greater than 4, and I know in a binary search tree all the values that are greater than the node will be on the right. So basically with two if conditions, I have found the node that I was looking for. Now if I had this in an unordered list, it would take me O of n to find that same value. So this is where the idea of a balanced versus unbalanced tree become important. So if we take a look back here, if I had an unbalanced tree where all the nodes were on one side, and you can have a binary search tree that is unbalanced. So I could have this 9 as my root and have 9, 8, 6, 5, 4, 2, all of them on one side. And that would not be very beneficial because at every iteration, I would only eliminate one node. So the idea of trying to balance a tree becomes important because of the time efficiency. Basically, every time that we iterate down, we eliminate half of the tree. Now let's take a look at the code for this. So if I'm trying to find a node with the value of 5 here, so my target is 5, I assigned my root to a variable called node, and I will go through this while loop as long as the value of my node is not target. And we're assuming that the target does exist in this tree. So all I need to do is if the value that I'm looking at right now is smaller than target, I go right. If the value is bigger, so it's just this else condition, then I go left. And this will do exactly what I described earlier until we reach the value, and this while loop will terminate at the end. To insert a node in a binary search tree, we can just trace the values and insert when we reach a place where there is no node. So if I want to insert 7 in the original tree in yellow, I start from the root. 7 is bigger than 6, so I go right. 7 is smaller than 8, so I go left. There's nothing, so I insert 7 here. If I want to insert 3, 3 is smaller than 6, I go left. Is smaller than 4, I go left. Is bigger than 2, and there's nothing, so I insert 3 here. So this is the basic way of inserting a node in a tree, and the reason I say basic is because this tree can become unbalanced if we use this approach continuously. Let's say I were to insert 10, 11, 12, 13, and so on. All of them would be inserted here, and this tree would gradually become more and more unbalanced. So there are more advanced way of inserting nodes and rebalancing the tree, which is out of the scope of this video, but it's good to know that there are data structures in different languages available that will allow you to keep a tree balanced. Earlier when we talked about DFS, we were really doing a pre-order traversal. And a pre-order traversal is where we take a look at the current node value, then we go left as much as possible. So we go as deep as possible to the left, and then we go as deep as possible to the right. So here we took a look at the root node, then we went left and left, then we reached nothing, so we went back up, and then right as much as possible, and so on. So that gives us the pre-order traversal, but we could also do in order or post-order traversal, which make a little bit more sense when we are talking about binary search trees. So in order will basically give you the value of the nodes in order, and that happens because we have a binary search tree. In a normal binary tree, these nodes would not be necessarily in order. And to achieve these three, all we need to do is to change one line in our DFS code. So let's take a look at this code here. The first part is the condition where we check if we have reached the end. Then this is the line where we could basically achieve any of these three. If I put it in the middle, this is basically where we are printing the value out. So if I put the node in the middle, then I achieve in order traversal. Let's print this out. So you can see that the values are 2, 4, 5, 6, 8, 9. They're in order. If I shift this to the top and then do my recursion between these two, so I'm first looking at the node and then left and then right, then I get pre-order traversal, and you can check to make sure these are the same. And lastly, if I put it at the end, so if I take a look at the current node at the end, so first I'm looking at the left one, so then right, and then the current node. Then I achieve post-order traversal. Binary trees are one of those concepts that are easy to learn but hard to master. I've left you a few questions in the description section. Have a go at them and try to gradually solve harder and harder questions. Best of luck.